Hey guys, and welcome back to another video on the channel. In today's video we're going to be solving an application of a differential equation. This is taken from an exam, and let's just get straight into it. So the motion of a pendulum of a clock satisfies the differential equation. The second derivative of theta with respect to time is equal to some constant g over the length times by the function theta. So they tell us that g is 9.8 meters per second squared, the gravitational constant, and L is the length of the pendulum, pretty much. Okay. Find the length of the pendulum if it is known that the pendulum swings with a frequency of 2 hertz and it performs 2 complete periods per second. Okay. So straight off the back, I know my function is a function of time and it relates to theta pretty much. So imagine you have a pendulum and it's swinging from side to side. Pretty much this angle in here is going to change as time goes onwards pretty much, okay? Now, this one is simple harmonic motion. The reason why is because simple harmonic motion is basically things that oscillate back and forth. So a pendulum oscillates back and forth. And the best way to describe something like that is with a sine or cos function. So I know for a fact that our function itself is going to be some sine or cosine function. So you can say it's either a sine or a cosine function and just label a couple things. So in a sine function, there's a couple things that the sine and cosine function, there's a couple things that are important. So for example, there would be an amplitude with our sine function, okay? There would also be a coefficient in front of the t pretty much. And we also have to account for any horizontal or vertical, horizontal shift. We could also write it exactly like this as well, where we have, some different coefficients. So let's just say, or we could say a cos of same thing here plus beta, where it's a different horizontal shift, because a sine curve and a cos curve can become one another if you shift it enough to the left or right pretty much. So you can use either model with this particular equation. The reason why I can use this model is because it is a harmonic system, because it's going back and forth, so only a sine or a cos curve can represent its motion pretty much. So something like this or something like this pretty much, and it can only be modeled with either one of these. Okay, so now we've got a general idea of it. I'm going to stick with the sine one, and let's just see what the question's asking for. We need to find the length of the pendulum, so hence we need to find what L is. Okay, so we have a differential equation here, and we have a setup of what our function looks like. Okay, so what I'm going to do is write my differential equation. So that's d theta on dt squared, and I'm going to move this to the other side, so we get negative g on L times by theta. Now this theta is my function itself. Now we need to find what our second derivative is. So what we're going to do is differentiate this with respect to time. So what we're going to get is d theta on dt is equal to, this is going to be a chain rule, so differentiate this inside function, so you only get omega, so you get omega a, and then you're going to have cos here, because if you differentiate sine turns into cos, you have a cos omega t plus alpha. Okay, now we have to differentiate it again because we're looking for that second derivative. So second derivative, differentiate the inside function, so you'll get omega again, so you'll get omega squared. Now it's going to be negative because sine, if you differentiate that, turns into minus, cos, if you differentiate that, turns into minus sine, so you'll get negative a sine of your original function. Okay, so now we have an expression for both the second derivative and our function itself. Okay, now we need to understand what this actual omega means pretty much. So this omega represents the pretty much a symbol in, it's like the factor that compresses our period in our sine function. So if we look at a normal sine function or cos function, it's the same thing. A sine function has a period distance of 2 pi. So when it's just sine of x, your period distance is 2 pi. If it was sine of 2x, your curve gets compressed, so it completes a full cycle in half the time. So for example, the period distance of this function here is just pi. So what that means is, in order to calculate the period distance, if we have sine of bx, you'll need to have 2 pi divided by whatever that b is. So for example, let's see if this formula works with this one here. So if we have b is equal to 2, the period distance is 2 pi divided by 2, which is pi, which makes sense with this curve here. Okay, it's the exact same thing with this stuff here. So instead, our period is represented with t in harmonic motion. Okay, but we still have this 2 pi divided by that coefficient in front of your independent variable. So in this case, t, so it will be omega. Okay, so this is an expression for our period in this particular situation here. So now I'm just gonna get rid of this. If you want to take a look at that again, just rewind the video. So now that we've got that, let's see what else we have in this equation. So we have the two parts for our differential equation, but we also have been given something else. Frequency is 2 Hertz, so frequency is 2. We also know the period is, it completes 2 complete periods per second, but that's actually kind of a double up information here, because if you have the frequency, we know frequency is 1 over the period. So that means if we put the 2 there, we'll get 1 over the period. So that means the period is half a second, which makes sense, because if it completes 2 periods per second, that means in 1 period it will be half a second. So that makes sense why t is a half. So what we have is t is a half, this equation here, and our differential equation. So what we're going to do now is substitute these bits and pieces into our differential equation. So what we're going to get is negative omega squared, a sine of omega t plus alpha, so this is my yellow bit, is equal to negative g on L and theta, so a sine of omega t plus alpha, and this is my green bit here, just this bit. Okay, now we can look at this thing and realize this is exactly the same as that. So what that means is this must be exactly equivalent to that. So that means negative omega squared is equal to negative g divided by the length. Now g is a constant and L is a constant. We can work out what omega is using these other equations up here. So we know these guys to be true. So what we're going to do is put this down here, and we're going to work out what omega is. So we can put in a half into this equation, so we'll get a half equals 2 pi on omega. So if we move omega over here, so we get a half omega equals 2 pi, times both sides by 2 to get rid of that half, so you get omega equals 4 pi. Okay, then we can plug this guy straight into here, so we'll get negative 4 pi squared equals negative g on L. Now we want to get L by itself, because remember we're trying to find the length of the pendulum, so put the L up there, so we'll get L equals negative g on negative 4 pi squared, so you just get g on 16 pi squared. G is approximately 9.8, so you can work out what that would be. So L would be 9.8 on 16 pi squared, so that's approximately, if we put that into our calculator, 9.8 on 16 pi squared, so you get 0.062. Now, what are the units for this? Well, 9.8 is meters per second squared. So that means this must be in meters if that was in meters. So that is the length of the pendulum in meters. Now they haven't specified what they want it in, but you can leave in meters or centimeters. I would convert it to centimeters because that's quite small for meters. But yeah, that's how you solve that question there. If you have any questions below, try and leave something in the comments and I'll try my best to answer it, and I'll see you in the next video.